Okay, yesterday we looked at the net ionic equation for precipitation reactions. So you see precipitation reactions from the new solid, and that shows the driving force for the reaction. You can see I've circled in red how those two nickel ions have a collision with the chromate, and they form a new solid, an ionic compound that drops out of solution. It's no longer soluble. For example, we took a look at this reaction where both of the products were aqueous. And so they all have collisions with each other, but none of those collisions lead to a substance that's insoluble in water. So when everything is soluble in water, when all of those ions are soluble, we have no reaction. So those are precipitation reactions. The other important thing about these reactions is that when we have a double replacement, so we're swapping the cations, forming a new solid, the charges don't change on the ions. So again, take a look in red. We start with an Fe3 plus and iron 3, and we change the cations and anions to form new compounds. But the charge on that ion does not change in a precipitation reaction. Next, we're going to look at reactions that involve changing the oxidation state. And those are called oxidation reduction reactions. That includes several types of reactions that we will look at. Oxidation reduction reactions have to do with charge on the ions can change. So the charge or the oxidation state changes. So we'll look at this first in our combination reactions. So here we're making a new ionic compound. Typically, now these are all happening without water. So these are, like in the picture, the magnesium is burning. So if you looked at the chemical reactions lab videos, you should have seen one of these going on in real time. So there's no water. It's not taking place in water. It's all dry. Magnesium solid. Grabbing oxygen from the air, it requires initiation. It requires a spark to start that reaction. But then it's just going to go and it's going to form a solid ionic compound. That ionic compound is going to be expressed as the smallest neutral subunit. So it will have a molecular formula in the equation that is neutral. So let's go ahead and do that. Now, again, when we form ionic compounds, they are neutral, so we don't show any charges on them. Instead, I'm going to write a different line. I'm going to write some notes. I know I'm going to use the charges to form the new compound. So what is the charge we form from magnesium? That one is in group 2, so it's going to form a 2+. Oxygen is in group 6, so it's going to gain 2 electrons to look like the nearest noble gas. And now those are going to form a new ionic solid that's neutral. That just requires 1 magnesium paired with 1 oxygen, and it's a solid. Think of salt. Think of sodium chloride. That's our typical ionic compound. That one is soluble in water, but it exists as a solid when it's not in water. Okay, now we have to balance. Oxygen is always diatomic, so we're going to need to form 2 of these formula units of magnesium oxide, and that will require 2 magnesium atoms. All right, so let's do that for these other ones. We're forming neutral ionic compounds. So what we're doing in this section is we're looking at redox reactions, specifically the combination. But we've already done this skill. We're practicing the skill we learned last week, which is forming neutral compounds, and that will definitely be on the exam. So you will need to be able to form neutral compounds. All right, potassium is in group 1, bromine is in group 7, so it's going to go -1. Forming potassium bromide solid, and again, bromine is diatomic, so we'll need to form 2 of those, and that will require 2 potassium. All right, and then the next one, aluminum is in group 3. Sulfur is right underneath oxygen. It's in group 6. So to form a neutral compound with these ions, we'll use the crossover method. Aluminum sulfide. These are all going to be solid ionic compounds because there's no water. Yeah, if we put it in water, it will dissolve and be aqueous. That's right. Okay, we'll just fix up the balancing here in 2 and 3. We have another kind of oxidation reduction reaction, and that is combustion. Combustion. So this means burning in oxygen. We're always going to see oxygen as a reactant. And it requires heat, right? We have to light it on fire and then it burns. So oxygen and heat, that's our clue that this is a combustion. And complete combustion always produces CO2 and water. So our products in every case are going to be CO2 gas. And then water, because it's at high temperature, it will be water as a gas. And then, for example, if you think about your car, you think about burning the gasoline in your car, then sometimes you see water dripping off the tailpipe. You see it dripping out the end. That's because all that metal cooled it down. So it was water vapor, and then as it comes out into the atmosphere, it condenses on the surfaces and drips off. But it's formed as a gas at high temperature. Okay, so when you notice that this is a combustion reaction, we are going to start with your carbon, balance carbon first, then balance your hydrogen, and the last thing you're going to do is balance your oxygen. So in this first one, we'll have 3 carbon over here. That means we need 3 here. And let's see, next is hydrogen. We have 8 hydrogen here. So let's put a 4 here because 4 times 2 is 8. Next, I'm going to write my oxygen line. So in this case, every time I put a coefficient in front, I'm going to get 2 oxygens on the left. So I'm going to write 2x. The arrow is my equals. And that 2 is because oxygen is diatomic. Now, another thing I like to do to make sure that I find any mistakes is I'm going to write my compounds separately. So 3 times 2, the carbon dioxide brings in 6 oxygen, and the water brings in 4. So now I have an equation I can solve for x. X will give me the coefficient in front, and that is a 5. So for something like propane, this is a propane molecule. 1 propane requires 5 oxygens to burn completely. Okay, so let's do the next one. Same products. CO2 and water. Okay, so looking at the carbons, you can get 5 carbons on each side. Then the hydrogens, 12 equals 2, and then that must be a 6. 6 times 2. So we get 12 hydrogens on each side. Then we need to look at the oxygen. So for oxygen, I have 2x. The arrow is my equals, and I have 10 plus 6. So we can just solve for x. X must be 8. Okay, go ahead and start on the next one, but notice now there's oxygen in both of the reactants. So this is like we have in our gasoline when we started putting ethanol in there, putting alcohol in the gasoline. We're going to see a lot more water comes out. We're still starting with the carbon. Then the hydrogen. Now here's where it's different. The arrow is still my equals, but I'm going to have 1 plus 2x. So that's the 1, that's the 2, and then x is going to be my coefficient. That is equal to, we have 6 times 2 is 12 oxygens from carbon dioxide, plus 3 oxygens from water. So we can solve for x. So I just showed my work on the margin. If you see the answer and you don't need to do that, that's okay. But make sure that you're very careful with the details. All right, the next one is a little bit more, has a little bit more to it. So let's take a look at that one. We'll start again with the carbon and then go to the hydrogen. And then for the oxygen, we have 2x equals 8 plus 5. And now we have an odd number, 13. So if we solve for x, what do we get? From this, we get x equals 13 halves. We don't allow any fractional coefficients. They have to be whole numbers. The coefficient in front of each compound has to be a whole number, the smallest whole number relationship. So what I'm going to do is I'm going to multiply everything in the equation by 2. So I'll go ahead and fill this in. This was 13 halves, but now I need to multiply by 2. And so for that answer, I'm going to get 2 C4H10, that's butane, plus 13 oxygens produces 8 carbon dioxide and 10 water. Let's talk a little bit about how we know this is an oxidation reduction. When we talk about oxidation reduction, that means the oxidation states or the charges are changing. So if you think about oxygen, it has 0 charge, it's neutral. And it goes over here to form O2 minus. So that charge has changed and it has gone down. So in this case, O2 is reduced, right? Because 0 went to minus 2, it went down. That means something must have gone up. It's going to be the carbon. The carbon oxidation state went up. I don't really want to worry about figuring that out right now, but I just wanted to show how you can tell. Another way we define oxidation is adding oxygen or adding bonds to oxygen. So when we're thinking about the carbon in particular, it goes from carbon with hydrogens. In this case, it's got 4 bonds to oxygen. That's pretty much as oxidized as possible. So that carbon got oxidized. All right, so I just wanted to bring in a little bit of the language about oxidation reduction and how can you think about, is this an oxidation reduction? Now in these cases up here, when we're looking at combination, we're going from a neutral element to an ionic compound. So you can really see the charge, right? The 2 plus, it goes from 0 to 2 plus, and this one goes from 0 to 2 minus. So again, the magnesium gets oxidized, the charge goes up, and the oxygen gets reduced. Goes from 0 to minus 2. So that's why we group these into oxidation reduction, and that's why these reactions are in their own chapter, chapter 9. We're still doing the same thing, though. We're forming neutral ionic compounds. Another kind of redox are decomposition. And for decomposition reactions, This is some compound breaking apart into simpler compounds, and we don't know how to predict that. We'll always be given the products. So with decomposition, you might see just one reactant. Often with heat, you see the triangle, it's often with heat until it falls apart and decomposes. We'll just recognize that those are decomposition and balance them. Now in this first one, I have that 2-3 mismatch. I can just lead off by making the oxygens equal. So here's our equal sign, and we want to make 3 of these oxygens equal 2 over here. So we can think about like a cross multiplying or the crossover method. We can put a 2 here and a 3 here, and that gets us 6 equals 6. Then we have 2 potassium, so 2 here, and then the 2 chlorines balances out. That one's done. In the next one, we have 2 aluminum and 2 aluminum, so that doesn't really help us. So let's look at the carbons next. Don't forget to multiply out anything in parentheses. So I'll give you a minute to work on these. Don't forget to multiply out these parentheses. So go ahead and balance those. If you want to pick up more time and more practice, there's an extra worksheet on WAMAP with just a list of equations to balance, so you can get good at going fast. All right, 3 carbons, and then I'm going to look at the oxygens. This has 9 equal to 3 plus 6. Okay, those are good. So this is a 1 and a 1. This one, the metal does help us, so we'll start with the iron because that'll change everything else. All right, let's do the carbon. We've got 3 times 2 is 6 equals, oh, just 1 carbon here, so let's put a 6 in front. And then carbon is done. All right, let's take a look at, is the hydrogen? Maybe the hydrogen is the next one that's easy because it only comes in over here. So we have 3 hydrogen in each formula unit and 2 formula units. So for hydrogen, we also have 6, and we just have it here. So we're going to have to multiply by 3. And then finally, let's take a look at the oxygen. I'm going to erase the carbon. 3 times 3 is 9, times 2 is 18. We have 18 oxygen. Here we have 3 and 2 times 6 is 12, and then plus 3. So that's done. We're done. That's a 1 in front. So lots of practice balancing, forming compounds and balancing. That's what we're practicing. So we're learning some different reaction types at the same time. We'll want you to form neutral compounds and be able to balance reactions. Now we're going to move to another reaction type, and this one is a single displacement or single replacement. This is a redox reaction because you might have a metal that has 0 charge, and then it's going to form some kind of a cation. So the charge is going to change in a single replacement or single displacement. Now, in this case, we have usually a metal, but maybe a hydrogen or another element with an ionic compound, and you're going to ask the question, does A bump off B and cause B to come out of solution? So the way we answer that question is by looking at the activity series. The activity series gives us the relationship of the metals and the way that they naturally behave. This is the same kind of property that allows us to build batteries. They just have different reactivity and a different amount of desire to give electrons or take electrons. So we will see this reaction happens when A is more reactive, more active than B. By active, I mean it likes to be aqueous. I'll make that a 2+ aqueous, right? So instead of being solid, it will react and go into the solution, so it's moving more. Maybe it's more active. That's one way to think about it. Okay, so this again, you always have on your periodic table right here. But for our class, I'm going to give you only reactions that go forward, right? So I want you to understand how this works and how it relates to everything. But for testing, I'm only going to give you reactions that go to products. So let's look at what's going on. These are really nice examples. And we see this in the lab. I know you didn't get to do the lab. But we have the video of the copper. So let's take a look at what's happening on that wire. We have the copper wire solid, and it's in solution. In our lab, we use silver nitrate, I believe. So what you see here is the net ionic equation. Because nitrate is the same on both sides, this forms copper nitrate. So we're looking at the net ionic equation. The nitrates just sit around in solution. They keep everything neutral. All right, so the copper wire is the solid. And as the silver ions come close to the wire, electrons are transferred. And the electrons are gathered by the copper and turn the copper, the copper releases the electrons and chemically dissolve it. So they release the electrons and then they dissolve into the solution to form that copper 2+ ion. So copper is more active than silver. The silver in solution accept the electrons from the copper and drop into the metal, drop into the solid, right? So that's what we're seeing. We see the shaggy silver crystals growing on there. And when you look at the copper ions, right, it turns that solution blue. So you can see the blue solution near the wire. So what we do in lab, we might shake that wire and the silver falls off and it exposes a new copper surface to keep the reaction going. So as you take a look at the videos for the chemical reactions lab, you'll see before and after. In the after picture, there was a watch class and it has a little pile of silver and then it has the copper wire. And the copper wire is all black and it's all, it's rough. It's been dissolved a little bit, so it's not fresh and clean. Most of the chemical reactions lab is the pre-lab and the post-lab, doing this work that we're going to see on the exam tomorrow. But the observations come from the videos and the photographs. So if you have any questions about that, let me know. We can go over it. Okay, so let's do these reactions, right? So we're looking at, and again, I'm only going to give you reactions that go. So zinc is more active than silver. It will displace silver. Let me just take a look at this series again. Wait, where'd it go? Here we go. Notice that these here, copper, silver, gold, those are the metals that we use for money and jewelry. So those are the least active. They like to stay solid. They don't easily dissolve. They stay solid. So those noble metals are the ones that are not active. When we look at acids, when we ask the question, will this metal dissolve in an acid, we're going to use the H as our cation. You can see that these ones here, 1, 2, 3, 4, 5, 6, right? 6 of them, not including magnesium. Do you recognize those? These are, they have their own name. These are the active metals. Where have we seen these before? So we have a couple places. One on the solubility rules. We have rule number 1 has these guys. And then rule number 10 has these guys. They're always soluble. Those are the ones that are always soluble. And we're going to connect that with our acid bases. Those are the cations that give us the strong base. So strong base cations have this shape on the periodic table. Remember I talked about that just briefly. We're going to see it again. So again, you don't have to know all of this right now. I'm just pointing out some of the trends to connect the different areas of chemistry so you recognize, why is this? Also, you might notice lithium is often in batteries, and it's so active. So that's one of the metals we see in batteries. Okay, cool stuff. So now let's put it into our chemical equations. Again, we're going to form ionic compounds. And when the zinc bumps off the silver is going to form the solid. All right, so zinc always forms 2+. Silver always forms 1+, and nitrate is 1-. So we're going to make a new compound between these two. It needs to be a neutral compound, so we'll have 2 of those nitrates. And now the other thing that's left is the silver. It's going to form the solid. So it's a single replacement. When we had a double replacement, we had 2 ionic compounds. But now we just have 1 ionic compound with a metal. It's going to be a single replacement, just the cations switch. Okay, we have to use our solubility rules. All nitrates are aqueous, and we have to balance it. And there, we're done. Okay, same thing for this one. We'll use the charges to form neutral compounds. Use your solubility rules. And then we're going to need to balance it. I see that 2-3 mismatch happens, so we can quickly balance the chlorines, and the metals will fall out from there. So for these ones, we had ionic compounds, but sometimes we might see an acid. And in that case, the cation is the H. So that's going to produce hydrogen gas. This reaction, we've seen the picture a few times of that strip of metal reacting in the water or in the HCl. So same thing, we have to form neutral ionic compounds, and then that element at the end will end up being the hydrogen gas. Because it's an acid, the cation is that H. This one is going to go to a 2+. This one has a 1+ and a Cl-. So we have to make our new ionic compound that's neutral. And now what happens to the hydrogen? It's going to go to its elemental state. So you have to remember it is diatomic, and it's a gas at room temperature. Need to make sure it's balanced, and we're ready to move to the next one. So if we look at the products, we see that we have one has 3 bromine, the other has 2 hydrogen, but they come in as a 1-to-1 compound with HBr. So we'll need 6 HBr to make both of those. So that'll give us 2 in front here and a 3 in front here, and that means 2 aluminum. Okay. We have another type of single displacement, and that is when instead of an acid, we're going to use water. And the only ones that react with water are the active metals. Again, the ones that are on this part of the periodic table. Those react with water, and they produce a basic solution. That's why they're called alkali metals and alkaline earth metals. They produce the base. They still form H2 gas from that water. They're going to form the metal hydroxide, which is basic solution. So calcium is a 2+. This is going to be an H connected to an OH, so we'll look at calcium hydroxide. Neutral ionic compound with 2 hydroxides for every 1 calcium. And then H2 gas. So you can think of water as that H with the OH. We've got 2 hydroxides and 2 H's. So we're going to need 2 waters. And that's it. Then it's balanced. Oh, all of these are aqueous. All of these bases are aqueous. So again, if we think about that H connected to an OH, we have 2 of these, so we're going to need 2 of these. Now the last one is looking at iron. Iron is not on this list. Or another way to say it, do the bike racks melt in the rain? No. Iron does not dissolve, so this is no reaction. Okay, let's see. Let's go ahead and get started on this. We have 5 more minutes. So let's go ahead and get started on the net ionic equation for this kind of reaction. When we talk about magnesium solid, right, we saw a little strip, a shiny metal strip. So that is not the ionic form yet. When it's by itself, this one is going to stay magnesium solid. Let's draw iron chloride, though. Iron chloride is aqueous, and what does that mean in the beakers? It means it splits apart into ions and they move independently. Okay, so let's run this reaction. The magnesium is going to displace the iron and it's going to combine with the chloride. By rule number 3, chloride makes it aqueous. And then the other one left over is going to be iron, and that will form the solid. Iron is less active, so it forms the solid, and it tends to stay solid. All right, let's balance it. And then after mixing, what have we got? Now we've got iron solid down here. And magnesium chloride. So let's take a look at what happens for that ionic equation. Now, iron chloride is ionic, so I'm going to go ahead and write that as separated ions, just like in the beakers. And on the other side, we have magnesium chloride is soluble. So that one's aqueous. We have 3 magnesium 2+ ions plus 6 chloride. And then that metal, that's just going to sit there. The iron metal, you have to write it the same way. Okay, so let's take a look at the spectator ions and see what cancels out. What about the magnesium? Take a look at the magnesium. Are those identical? The same things? No, those are different. Magnesium solid is different from 2+ in the aqueous solution. So those are not going to cancel out. What about iron? It's different. They do not cancel. What about chloride? Those are exactly the same. So those are the spectator ions that cancel out. So let's write our net ionic equation. We have 3 magnesium solid plus 2 Fe aqueous, 3+, goes to 3 magnesium 2+ plus 2 iron solid. Those are totally different, right? One has a magnesium solid, the other one has an iron solid. And these we can think of as that transfer of electrons. We can show that transfer of electrons. So notice that the total charge is on this side. So if I look to balance the charge, I have 0 on this one and a total of 2 times 3+ on this one, 3 times 2+ on this one, plus 0. So that charge is balanced. There's no free electrons. All of the electrons that magnesium gives are received by iron to make this happen. So maybe we'll look at those half reactions next time. We'll see. Oh, and then we'll jump into acid-base.